Thank you, everyone, for joining us for our next GoAERO expert lecture with Dr. Sanjiv Singh. We're so excited to have all of you here. We are, of course, so pleased to be joined by our partners and supporters, along with our partner organizations from all around the world, including France, China, the UK, and Italy, and all across the US. It's my pleasure to introduce Dr. Sanjiv Singh for our expert lecture here today. Dr. Singh is a consulting professor at the Robotics Institute at Carnegie Mellon University and the CEO of Near Earth Autonomy, a startup that develops autonomy for next generation aircraft that will inspect infrastructure, deliver cargo, and transport passengers. Dr. Singh started his career in 1985 working on the first autonomous ground vehicles to operate outdoors. Since then, he has led research and development efforts with applications in aviation, agriculture, mining, and construction. In 2010, he led a team that demonstrated the first autonomous full-scale helicopter capable of takeoff, landing zone evaluation, and safe descent. In 2011, he led the autonomy effort for Transformer, DARPA's flying car program. From 2012 to 2017, he led the perception efforts for ONR's AACUS program that demonstrated high-performance autonomous rotorcraft flight in austere environments. Dr. Singh obtained his Ph.D. in robotics at Carnegie Mellon, and he is the founding editor of Field Robotics, a new open access journal, a TEDx speaker, and a co-founder of 4 companies. Join me in welcoming Dr. Sanjiv Singh.
Thank you, Nidhi. That's great. Let's see. It's a good time for me to share my slides. Give me a second. Can you see my title slide?
Perfect, thank you.
Okay, so before we get started, I want to mention 2 things. One is I was told to consider the idea of talking about sensors as relates to remote and autonomous low altitude flight, but not really actually try to address the exact challenge problem that GoAERO is posing. So I'm trying to stay general. I won't be making any specific recommendations to the rules or any of the concept of operations there. And the second thing is that I am going to show some specific sensors. I'm not showing them because I'm endorsing them or something like that, but I want to give people some idea who are not aware of these kinds of devices, the scale at which they operate, the kind of data they generate, the cost, size, weight, that kind of thing. So no endorsements to any specific product. I'm going to just give you some examples. Good. Thank you for that introduction, Nidhi. I'll get started by talking a little bit about this challenge. I had a look at it briefly to understand this, and it occurred to me that there's something kind of unique about this challenge, which is that it requires both a flight in complex obstacle-rich environments, and then second, the scale of the aircraft is to accommodate humans. Okay, so we've seen aircraft that can do one or the other, but to be able to do both of them is sort of really interesting in this challenge. So first, this is some mixture of aviation, next-gen aviation, and robotics, in the sense that this is just happens to be, will be probably best thought of as a flying robot, that it is able to perceive the environment, is able to act on the information that it's gathering in real time and get to its goal. Okay, so that's just a little bit of setup for this. That's how I'm going to think about this, because my background is in robotics. I'm going to try to relate it to basic first principle thinking about how we develop robots for outdoors, whether they're legged or wheeled or flying, is sort of like, it's nuanced there, but there's some common themes there in terms of how these machines understand the environment and act upon that information in real time. So one thing to get started was I was trying to think about when we've seen something like this. Has this ever happened? It's kind of interesting. I said it was unique, but there is an example that I'm thinking that most people of at least a certain age would be aware of. And if you are not aware of this clip I'm going to show, which will do this, which will demonstrate this kind of thing, I'll give you the reference. So here we are. Here is a flight. Okay, it's in a fairly unstructured environment at high speed. It's not just the person here who's flying, but of intelligence, some sort of a intelligent aircraft that is helping be able to fly both fast and then stay safe. So that never happened in reality, but let's see what did happen. I was involved in a project from 2017 on for a couple of years, and here is something that we actually sought inspiration from that Star Wars scene, but this is an actual, honest to goodness, autonomous aircraft that's flying in an unstructured environment. It's been told to go a certain distance, maybe a few hundred meters in the front. And then what you see is intertwined in between these video clips on board and off board is how it's reasoning. So it's flying, it's estimating its position, it's mapping the environment, it's actually using that information to be able to guide itself safely through this environment. And here you see kind of a playback of that scene here. The blue line is the path that it took, and then this is the environment that it created, the map that it created at the end. So to give you a sense, it flew 300 meters. There was no map to start off with. It was just told to go straight, and then it was able to guide itself to get there. Okay, so that's just some state of the art. This is already now 7, 8 years old. And of course, there's some discussion about it in the literature about this. Not done at human scale, but this is meter and a half scale flying aircraft. Okay, so I want to suggest to you that there are sort of like some problems that we solve over and over in robotics. It doesn't matter what kind of robotics, especially robotics in the outdoor environments. And they are essentially 6 problems, I'll say. One is, where am I? The other one is, what's around me? How am I doing? And then how do I get to the goal, knowing where am I and what's around me, and how the vehicle or the aircraft is actually performing in real time. There's also these other 2, like how do I improve, which is a machine learning problem, and how do I cooperate to do more, which is with more agents, which is teaming. I suspect that most teams who are going to solve this challenge are going to work on at least the first 4. They're going to have to do some version of those. For today, what I'm going to focus on is on these 2 issues, which is solving the problem of where is the aircraft at any given time, and then what's around me, which is the aircraft, such that it can perform safe flight and can avoid anything in the environment that might be there. And I think you have elements of that in this challenge. So I think we'll focus on sensors and awareness for these 2 problems. Okay. Now, if you switch from that very high-level view that's common to just about any robot operating outdoors, and you think about mapping this to BVLOS flight, which is beyond visual line of sight, which means that you press a button and the vehicle just flies, and it deals with all sorts of things that might not be in the plan. Because if you knew something was there, like you knew there was traffic of other aircraft, or you knew there was something in the world, you would have already planned that. So I'm just going to walk you through these kinds of modules here that any aircraft will need to have if it's going to do, the kind of first response in civilian airspace eventually. We might not need every one of these modules in the competition, but let's just go through these. So first, something, possibly a human or a computer, is going to decide, okay, you're going to go here, and by the way, you're going to go through these kinds of waypoints. Stay out of these areas and go through these points, for example, for just very high-level specification of the task. We call that mission planning. A second problem to solve is, we call that obstacle avoidance, which is basically the aircraft has to recognize objects that are in its flight path that are, in this particular case, I'll call obstacles as things that are stationary, that are not moving. And so, of course, if you knew about them, you would have guided the vehicle around them. But since they're unknown, the vehicle has to, in time, understand these kinds of obstacles and then guide itself without having an operator tell it to do so, be able to stay safe from colliding into these objects. Now you have collision avoidance, which is essentially detecting and avoiding other aircraft. It goes by a couple of different names, sometimes just called detect and avoid, sometimes called due regard. We call that collision avoidance, just to distinguish it from obstacle avoidance, which is essentially, this is detection of other traffic that might be in the area. Now, sometimes the traffic is going to be cooperative because it's going to be squawking and it's going to be telling the world where it is, but sometimes you will not be able to rely on that. So a first responder should be able to deal with any kind of traffic, glider, drone, helicopter, GA aircraft. Usually commercial traffic will stay away from the kinds of places. They usually fly pretty at high altitude, except for the final approaches, the takeoff and the final approach. But the idea is that the aircraft has to be able to detect all possible traffic that might be flying and be able to avoid that also. GPS-free navigation has to do with the idea that we'll talk more about GPS, how far it's come, but GPS is vulnerable to failure. In fact, GPS is known to have a 10 to the minus 5 kind of failure rate, which means one time in 10,000 hours. Let's see, 100,000 hours, 10,000 hours, 10 to the minus 5 anyway. You will have one serious GPS fault. So that means that if there's a problem with GPS, either it drops, either their GPS signal is degraded or GPS signal is jammed. If you have a problem with a satellite, you don't want the aircraft that are flying around autonomously to fall out of the sky. So what a eventual system will need is to be able to deal with the case where GPS is either degraded or unavailable. Contingency management has to do with dealing with all possible things that might go wrong in the aircraft. It might be a battery that fails unexpectedly. It might be a fire on board. It might be the loss of some sort of critical element on board. But the aircraft has to be able to recognize that something is off, such that it requires that it will be able to come to a safe landing very quickly based on the urgency of the failure. So to do that really requires a very careful planning before the aircraft takes off, which says, if I'm here and the aircraft fails, I'm going to land here. If I'm here, aircraft fails. All throughout for the entire aircraft, the entire path from takeoff to landing, that contingency plan needs to be done. And then if there's a failure, it needs to be managed and vehicle needs to be brought down safely. Precision landing is about being told the ability to land at a specific place, like some sort of a marker or helipad or any kind of landing pattern like that. And safe landing is to ensure that the vehicle does what a pilot would do, which is if it's told to land somewhere and something is occupying that space, then it registers that, it figures that out and then lands safely close to it. Okay, so what I'm going to say here is that what the main message of my my talk is going to be that for all phases of flight, accurate and smooth navigation is fundamental. Okay, and there are different kinds of navigation. You might achieve it in different ways, but you're going to need it for every piece. Each of these functionalities is going to require both accurate and smooth navigation. Detection of hazards is not only a matter of using sensors, but it's going to require composition of the sensors over time. So you can't just imagine that the sensor, for every particular case, a sensor will be able to see it in an instant. A hazard, for example, a tower or a building or some vegetation, it might require this over some time to composite that information. And that in turn requires that you have smooth navigation, smooth and accurate navigation throughout the flight. So that will be the common theme here in terms of what sensors are needed. Okay, so just a thought here, we are looking at 25 years since 2000, and just some thoughts on the sensors we're going to look at, and then some idea about computing and how much things have changed. So if you look at IMUs, and I'm going to just talk about not the highest accuracy IMU, I'm going to talk about like low cost kinds of versions of this. In 2000, we were talking about 100 degree per hour MEMS IMUs, and now you can get 10 degree per hour IMUs very easily. GPS at low cost was 10 meters. Now sub-meter is very possible. Lidar, 25 kilohertz Lidar, which would mean that 25,000 measurements from a Lidar were sort of standard at that time, and now a megahertz is very, very, very doable in a very small packet. Radar was mechanically scanned. Each beam was about 5 degree field of view. Now we have phased array, 1 degree. I'll give you some more details about examples of these. Camera dynamic range often interlaced, and 8-bit dynamic range. Now we have about 12 bits of dynamic range, and that what dynamic range means is how much variation you can see in the lighting. Now you can deal with both dark and bright situations, and how much range do you have? So you could do with 256 gray levels, and now about 4,000 gray levels in one scene itself. Okay. Just to compare, in 2000, 100 megahertz was a standard small processor. Now a couple of gigahertz is possible. So if you look at the multiplication over time, computing has gone very, very fast. These other sensors are, making tremendous progress, but okay, 1 or 2 orders of magnitude less than the computing itself. That should not be surprised because of simply Moore's law, right? Okay, so I'm going to go through each of these things in a little bit of detail, a bit boring, dry, but if you watch this later, you might want to look at it. But I think it'll be useful to talk about each of these sensors as sort of like where they fit into an autonomous aircraft that's aware of its environment. So first thing is that, we need to be able to figure out where the aircraft is smoothly and accurately. So one idea is to combine IMU and GPS. IMUs give you sort of smooth outputs, but they tend to drift. Their IMUs are something like what you have in your inner ear. So you can do odometry with IMUs, but that odometry actually drifts pretty quickly. So it's a natural to combine it with GPS. GPS triangulates signals from multiple satellites. It's a little noisy at any time, but it actually does not drift over time. So you can combine IMU and GPS to get both smooth and to get a smooth estimate without drift. Now, this presumes that you have good GPS signals. If you have either multipath due to being in a complex environment, like if you're walking around in Manhattan and you've ever tried to get walking directions on your phone, what you'll see is your position jumps around a lot, and that's because the measurements to the satellites, line of sight to the satellites, is occluded, and signals bounce off of the building. So you often get this thing we call multipath, and you can actually jump. So if you have at least 4 satellites, clear line of sight to satellites, then you can get pretty good smooth estimate without drift. So just to give you an idea, and again, I'm not endorsing this particular component. I just thought I'd give you an idea of sort of state of the art. Less than 100 grams, about $3,000. This is a something. I guess I don't know the exact size. There's a few inches by a few inches. but it is able to provide you both GPS and IMU and give you a combined output there, and even be able to take two receivers. So why would you want two receivers? What we call dual antennas. And the reason is that, of course, GPS gives you position. It doesn't give you orientation. After you've been moving for some time, of course, you get orientation from that. But with dual GPSs, if you have a separation of like, half a meter even, you're able to then instantly get an independent measure of orientation because of the accuracy of these two positions at these two antennas. And this is extremely helpful to determine orientation when you're starting. So when you start, it's, the vehicle knows its position, but without a dual antenna, you'll have to use some other means. Sometimes people use magnetometers, but really, actually, magnetometers are prone to failure in all sorts of environments, including the environment of the motors starting up. So dual antennas work really well to be able to get that first. Okay, this is where I am, and this is where the aircraft is pointed, such that it can get going at the very start. It might seem like a small issue, but this turns out to be something that bedevils a lot of aircraft, and you can save yourself a lot of hassle by choosing a component that already takes two dual antennas. Okay, Lidar is something that has huge progress over the last 40 years since I started working in autonomous vehicles. In the last 20 years anyway, we started to get some things which are sort of like, Coke can size, and then, like about half the size of a Coke can. So this is an instrument which weighs about 500 grams, costs roughly about $5,000, and there's various different variations on it. But what's amazing about this is, in this very light, very tiny kind of sensor, you are able to get 500,000 to about 1 million measurements of range per second. Okay. A typical configuration is 360 degrees. It's kind of like a lighthouse. So the lighthouse that is actually rotating, and the 30 degrees is along the vertical, the 360 in the horizontal, and you're getting range measurements at an extremely high rate. They're typically in the plus or minus 5 centimeters at this scale, not good enough to make really great maps, not good enough to do some sort of survey grade kind of measurement, but plenty for the aircraft to be able to understand the environment. So I was showing this picture here. This is an early work from about 2015, 2016, where we started flying one of these early version of one of these lasers on an aircraft that went, you can see where it starts in green and then it turns into red. So where it starts is green, where it ends is red, probably a couple of minute flight in a very difficult, complex environment here. But what you see is that it is able to, the accuracy is good enough that on board in real time, we're able to produce this kind of what we call a point cloud. Okay, point cloud is just basically a registration of all of these measurements into a common frame, such that you can then understand something about that environment. The aircraft is able to put these things together and then form a representation that it can use to stay safe as it flies. Okay, so that's LiDAR. It's pretty common, huge advancement from the self-driving car world. Radar, everybody understands radar because, radar is now available if you have a mid-range car or SUV that might, keeps it from colliding with cars ahead of it. But there are radar now that are being used for aircraft. And, this is a fantastic way to be able to detect other air traffic. It works much better with air traffic than with terrain. What's great about it, works in most weather conditions, works best at about 500 feet or above, just because as you get lower, as the terrain varies, then you can get false positives from the terrain below 500 feet. Gives an idea of like the ranges at which you can detect other aircraft. A small drone, you might detect it at 750 meters, a bigger drone at 1 kilometer, and then a GA aircraft at about 2 kilometers. It's super lightweight these days, less than a kilo, definitely about 500 grams. and not cheap, somewhere between 10 and 20K if you want to buy one of them. But, phased array radar, nothing mechanical moving inside there, and can detect even small things at some distance is a huge advantage to keep the aircraft safe from other aircraft. Okay, cameras seem to be obvious, right? Okay, we should use cameras. Why wouldn't you use cameras? Because humans have cameras, right? We have vision sensors. So what's available today is solid state, meaning that the image is exposed all once. So at least the pixels inside the image don't need to be registered versus each other. They are high res, which is a small camera could easily give you a 10 megapixel, and you don't want anything more than that. Maybe even a few megapixels is good enough. And they have this 12-bit dynamic range. What used to happen was with the lower dynamic range cameras, we could either see very brightly lit areas or very dark areas, but we couldn't do both of them. With the gain control, automatic gain control was never quite right. And either the camera is completely saturated or it was completely dark. And now you can actually do a really good idea. So really good job with these kinds of things here. Some of the cameras are actually not global shutter, which is they're exposed at once. They're not solid state. They're actually rolling shutter, and that makes machine vision a little bit more difficult. So rolling is global shutter cameras that are exposed, each image is exposed all at once, is a little bit more expensive, but totally available today. So, there's two things you can do with these cameras. One is you can use them to avoid things. You don't need Lidar or radar, right? Why don't we use cameras? Well, there are a couple of problems. One is that collision avoidance requires that there's optical texture. And I'll explain what that means in a second here. And it requires that there's enough separation between the cameras. So if you take a look at this drone, it probably has a separation between these cameras of about 30 centimeters. And this will typically be able to see about 10, 20 meters out. So in the perfect case, it'll be good for objects that are 10 to 20 meters if you're, if that's the range that's acceptable for you. But generally speaking, that's not for flying at things you'd like about 100 meters at least to be able to look at. So you need a very large separation in the between these cameras in the very best case. The other thing is optical texture. That means you need to see visual features like little cracks or spots or something else like that's naturally occurring in the terrain. So you have something that's a very brightly lit scene or dark scene, or you just have a area like a wall that has no texture on it, then you can't use binocular vision to be able to get a sense of depth to that object. What you can do very effectively is you can use cameras for improving IMU performance through a task we call visual odometry, and I'll just show you one. There's two cameras here. There's a camera pointing forward and there's a camera pointing backwards. And what we're doing here is as we go along, we are tracking features. They're just naturally occurring features. The system is able to find these features and track them. And what's happened here is use the IMU and the camera features recognition to be able to improve the state estimation without GPS. Okay, so the IMUs are going to give you some kind of characteristic. These days, IMUs are getting so good that this is less necessary, especially if GPS is out, but you can always augment your IMU, whatever IMU you have, by adding this thing called visual odometry. It's some sort of dead reckoning using these features. And this is actually a kind of a state-of-the-art algorithm that looks both forward and downward. So this requires there to be optical texture somewhere in the scene, not everywhere in the scene. And specifically, it doesn't require, as obstacle detection do, like the visual texture to be on the thing that's going to come and eat your lunch. So that's visual odometry. So what is GPS is not available? I just want to give you a little bit of sense of how we did that flying through the forest thing. We could take inertial measurement, feed that to visual odometry, feed that to laser odometry, and then possibly to laser mapping so that you can actually then match to the map that you're continuously making. I don't have time to go over the exact details, but there's a lot here going on in this area. So here's just a test we did going really fast. Okay, maybe going close to what, I don't know, something like 100 kilometers an hour or something like this down a street. What you're seeing here is there's visual odometry on the top right. There's laser odometry at the bottom, and we're combining them to be able to figure out where things are and to create a map of these things in real time. So here is the thing. You can see some vehicle going through a residential area at much higher than speed limit. I was not there to okay that. Thankfully, I was happy to see the result, but I was very happy nobody asked me if this could be done. But you can build this beautiful map as this thing is even going very fast, and you can see a lot of detail. This is simply I'm you, a camera, and a low-cost Lidar. Okay, so you can do that. This is state of the art now. Now that was just somebody driving the car, but here it is coupled with control. So this is doing all of what I said. It's building a map. It's registering to that map that it's building in real time. It is guiding, and then finally guiding the vehicle such that it can stay on a trajectory. Okay, so here you see a map being built, and then a very stable flight as the vehicle is flying a route. It's flying a couple of kilometer route. I'm just going to go to the end of that, and this is also good 6-7 years old. So you see the vehicle come to a landing, and then you'll see the map that was produced online. This is not developed after the fact or anything else like this, and the map was available in case something was came up while the vehicle was flying. Okay, so the one issue that happens is sometimes you have so much data that you actually want to not be drowning in data, and you have to think about how you keep the data and be able to deal with dust and rain, et cetera. So we have a framework we call an evidence grid, and this is going to show this with relation to a helicopter, full-scale helicopter that's flying, and it's taking all the laser hits and building up this sort of Minecraft view of the world. And the idea is that the Minecraft cells are essentially, they are based on some evidence over time. So if rays pass through a cell, then you reduce the probability of being occupied. If it stops in the cell, you say, okay, that's occupied, and you can build this kind of representation which has constant complexity. So basically you're planning around that kind of representation, not having to deal with the fact that if you start getting a million points per second, very soon the compute is going to run out of memory. I'm going to show you an interesting video of landing. So this is a place to show you the aircraft is told as it's coming in to land in this very complex scene. There's water, there's bushes, there's trees, there's a pickup truck, there's even a kind of a box that's sitting there. And the idea is without it hovering, the aircraft needs to come as it's coming, build up a map, evaluate that terrain, and then be able to figure out where it is safe to land. So here's that process happening. Aircraft is told go land there for whatever reason, either emergency or it just needs to land there. And you can see that it's getting its laser data registered into a common reference frame, and then be able to evaluate places that are level, they're smooth, they're obstacle free. Luckily, water does not reduce any, does not give you any returns back. So you just detect water by absence of returns. And here it is, it's found a place in that area that is not a tree, not a bush, not water, not on the top of the helicopter, and it finds a safe place to land. Here's another case here with a very interesting vehicle. It's a hybrid VTOL, which has got fixed wing to be able to move forward, and then it uses rotors to go up and down. So this is always fascinates me, an aircraft that kind of stops and backs up. It's uses its Lidar on board to create a representation that tells it where is safe place to land, and you can see it back up to the green zone, nowhere near the vehicle or any of the tents or anything else like that is acceptable, and it backs up and lands there. Okay. So we were talking about GPS, et cetera. So, what I showed you was if you are in a very complex environment, like a bunch of buildings, it's actually flying without GPS is easier in that sense because you can sense sense the environment all around you, and that helps you constrain. You see, as you fly, the aircraft sees different parts of that terrain, of that thing, the objects around it, and can match that. So, for example, there was a DARPA program to do flight inside a warren of tunnels. Here, you could fly 10 kilometers and, max nav error is less than 10 centimeters. The opposite is to fly at high altitude at like 400 meters. Then you can use visual odometry. You can match the terrain to some terrain database that you have. That works okay. But the issue is, what if you're doing, you don't have GPS, either not at all, or it's absent during parts of your thing, in a more typical kind of a elevation for urban air mobility, which is about, I don't know, 100 meters or so. But in this particular case, we're going to do an 18-kilometer flight over 50 meters. So this is what it looks like. And here's just a playback. This is Google Earth playback of that real flight that tried to maintain 50-meter kind of elevation as it flew about 18 kilometers. So it went over a river and finally landed in an airfield here. So you can see that. And then what you see here is green is the ground truth. If you just do visual odometry plus IMU, they're a couple of 100 meters away. But if you can add a terrain match to it, like you get a digital elevation map, and you can match your laser returns to that, then you can get to about 10 meters here. Okay, I think I'm going to end here, and I have one fun video to show. I think I have time, and then I'll be open for questions. So this is a fun thing here. When we were testing our thing in an orchard here, because you don't want to be testing it in a first in a live in an urban environment or even a suburban environment. We were testing it at a fruit orchard. There were rules, like you had to fly in such a way that there's always an observer who could take over. So the question is, like what's too fast, what's fast, and what's too fast. So here is I don't know why this jumped here. So we have a group that chases these things, and they have to go behind the vehicle. So there you are, chasing the aircraft, so that you can continue to monitor it while it's flying. So I'm going to stop here. I think I'm exactly on time, Nidhi, for some questions. Is this a good time? I can, of course, talk endlessly. I have the DNA of an academic, and my job is to make sure that I don't run over, so that I could do this. Hopefully there was some coherent thought here, but certainly if there were some questions, I'm open to them.
Absolutely. Yeah. Thank you so much, Sanjiv. Chock full of information that you've provided to us here. So we have a few questions that have come in. If you can please, all of the participants, utilize the Q&A function in the Zoom webinar and post your questions. We'll make sure that we have an opportunity to answer them. So a question being, let's see,
Nidhi, 1 second. Should I just stop the sharing? Because, I mean, I can go back to doing it if necessary, right? Should I stop it, or should I?
Absolutely, if you'd like.
All right, let's do that.
Perfect.
Okay, go ahead.
Is there open source software to do object recognition that would benefit the competition or those participating in the competition?
I think there is. There is recognition. So some of it is trained on some stuff comes, some of this open source stuff comes with some base level recognition of common objects, but then in addition, you can in fact train on top of that. Now, I tried to think about whether that's an important thing. Of course, you're free to formulate whatever you want to, but I think that unless you're an expert in machine learning, that may not be the first place for you to go, because sometimes these things are wrong. Sometimes they hallucinate. It takes some time to actually get them, even though there is open source software. The fact that there is open source software doesn't mean it will work out of the box, right? There's a fair amount of effort to get it to do what you need to do. So the question here is, hey, can you do it? Can you do your problem? Can you solve your problem without going there? I showed you the kind of 6 problems we end up solving, and machine learning was like the 5th kind of thing. And I think that it's really good for recognition problems. And if you have a recognition problem that you can do, you have a lot of training that you can set up, then maybe you want to go there, but you want to try first. My suggestion, try to do it without that, and you can always add that on.
How do you register the Lidar with it being not solid state?
Yeah, so that's a great question. So the Lidar data is all taken kind of from a slightly different place, right? And so what we're doing is that the state estimation system is working typically at at least 100 hertz, maybe more than that. So if you think about each laser element and the time that it is, you can interpolate between those two things. So let's say, let's say it's a megahertz, right? You're getting 1 million points per second. Now, not every single data is taken at exactly this at a different place, but let's say it is. So what you would do is that each of those points, those range measurements would be associated with a time, and you can look up in your state estimation where the aircraft was at that time. And so what that means is you have to have a fairly accurate, high resolution state estimation system that is giving you position and attitude of the aircraft as it's flying.
So Sanjiv, another question is, do stereo multiple cameras help? Do the benefits warrant the increase in complexity?
So I addressed that explicitly. Let me say that again. The problem with stereo vision is twofold, okay? And let's say you have a perfect world. A perfect world is one in which you have lots of what we call optical texture, like nice, interesting features all over the world. And outdoors, you do have that in many cases, but especially if you're looking at the sky or if you're looking at anything brightly lit, you may not have something. So, the case is that it's often there, but not there, not enough optical texture. But let's say you had good optical texture. So the question really is, what's the furthest out that stereo cameras can see? Okay. And there's an equation that you can look up for stereo cameras, binocular disparity. And how range works is you find a feature, or the system finds a feature in one image, and then it finds the same feature in the other image. And then through the disparities, one is at column 300 and the other one is at 280, then you say, okay, that's a 20 pixel disparity. You put your focal length in there and the baseline in there, and you can compute, okay, what the distance of that feature is. Well, so the question here is, where do you get epsilon disparity? Where is that smallest disparity that you can do? And actually, it turns out you can do subpixel disparity, okay? But it turns out for most practical cameras and most practical separation of those cameras, that is only 20, 30 meters away. Okay, so that means that if you use binocular cameras or trinocular cameras, you're going to be detecting 20 to 30 meters away. I mean, this is a heuristic. Of course, you can separate your cameras further. You can get higher resolution cameras. You can, do a few different things. Focal length can change and you can extend it. But generally speaking, let's say 20, 30, 40 meters is sort of what's practical, because the cameras have to be rigid with respect to each other. If they're sort of like, if you make the baseline too long, then they're sort of like bouncing with respect to each other, and then you cannot compute the depth at that point. So the idea is that from a practical perspective, typically for flight, and you can figure this out for your vehicle, if 20 meters, 30 meters is good enough, then maybe you can use, and you have good optical texture in your scene, then maybe binocular cameras are fine.
Do you think our Lidar, IMU, GPS, radar components must be implemented or integrated in order to compete in this challenge?
Sorry, I don't understand that question.
Yeah, so I think maybe if the person who posed the question, if you wouldn't mind clarifying a bit, but I think they're asking that the sort of detection components you mentioned, LiDAR, IMU, GPS, radar, are these components required? Should they be implemented when teams are looking to compete in GoAERO?
I think I was told to not answer that question.
Yeah.
Look, I'm what I did was I tried to point out some fairly recent technology that people who don't work in this every day might not know about, and the format and the cost of these kinds of things, right? So if I were to tell you about a LiDAR that cost $1 million and did amazing things, that's like practically useless to you. So I looked for components that are relatively low cost. The radar at the small form factor is a little expensive these days. It's 10 to 20,000. So that's on the expensive side. You might not need it because you might not be flying at altitudes where radar needs to be detected. But the idea here is that the other ones, the cameras and the IMUs and GPSs and the LiDAR, they're all relatively affordable. So now the question, should they be used? Well, okay, that's up to you. Right? I mean, is this the right answer here? I mean, I was told don't solve the problem for the teams, give them the base technology, and then they have to use their thing. But the question, if you're asking, is this technology usable for the challenge? I have picked among hundreds and hundreds of sensors that we are doing, because this is what we do. This is what I do 24/7. And I live this world and I've been living it for a long time, is that yes, it is suitable to the kind of world. Whether you use it or not is your choice.
I think that's absolutely the right approach, Sanjeev. Thank you for those comments. You've provided the knowledge and the information to the teams, and now it's up to them to sort of look deeper into each of these components and determine which one, if any, would be most applicable to the aircraft that they are designing and that they're building. Let's see. What is the key driver in most efforts? Perception, precision, perception range, processing speed, other.
Yeah, so I think that what you're looking at is a combination of things. What you want is you want to be able to detect the kinds first you want to be able to detect the the worst kind of hazard in enough time. Okay, and of course you want margins on there. So let's say that your worst thing was like a 1-inch cable, 1-inch wire. I'm not saying it is, right? Because I don't know if I actually haven't read the details. So there's a 1-inch wire somewhere in your thing, and your path is going to go through it, and you have to make sure you avoid it. So you have to think about, well, if I have a 1-inch that's the worst kind of object I have, because anything else is just going to be better than that. And then to be able to avoid it, I need to be able to detect it I need to be able to start maneuvering to do that at X meters. Then I want to be able to start to detect that at some other range here. And so then, it's a combination of, can you carry that sensor? Can you, will it give you that kind of range? Will it, do you have the computing to deal with it? So, there isn't usually a kind of a thing here to do it. Sometimes these problems can be so difficult that, one requirement drives everything. But generally, I think that the challenge is not going to be so exotic. What you're going to do is you're going to find the least detectable object, and you have to think about how far out you need to start maneuvering, and then give it some sort of backup from there, the distance that will be needed for you to be able to detect that, and then that's going to narrow your sensing modalities. And you come at this from a kind of like 5 different things have to work for this thing to work, to be able to stay safe. And then you have to do it every time, right? It's not, hey, can I detect this once and take a video of it? But, every time I fly and there is some object in your scene, you have to be able to detect that, and in enough time that you can maneuver to avoid that. So typically it's a set of constraints that come together. Dan may be gone, but tell me if I answered that question, Dan, if you're there.
So the next question, Sanjeev, and I think it might be our final one for now, is it seems that speed versus risk is the key choice for a given set of hardware. What metrics do you in the industry typically use?
Yeah, we don't think of it that way. We don't think of speed and risk that way. Generally, we tend to think of aviation is a big safety game, so you want to sort of like think about extremely high probability of success every time. And the way you do that is you put margins on everything. So if you think something can be detected at 50 meters, you say, okay, I'm only going to count on detecting that at 30 meters. If you think that you can maneuver from a particular distance, then you add some sort of time that you're going to have to maneuver from that. And you build in lots and lots and lots of buffers in every stage of the game in terms of the amount of computing it's going to take, in terms of thing, and then you build up a way to sort of like make sure that you can do this every time. We don't think about this in terms of risk and say, okay, this much risk is tolerable, because there is no easy way to think about that. Like, okay, if we did this set of parameters, we would lose 1% of the time. If you did this, it would lose 10% of the time. We don't have a quantification of risk that way. So we try to be extra, extra, extra safe in our world. So what's happened is that, this has been the world. I mean, I've been essentially working on outdoor robotics since the mid 80s. There's a kind of a magic moment that happened around like about 10 years ago, where computing and sensing and aircraft all sort of like, there was a moment where all of this stuff became relevant. Okay. Earlier, the elements were so heavy that you couldn't carry them on a reasonable aircraft. So we couldn't do a lot of these kinds of things, or they were too expensive, so most people couldn't afford them. And then so suddenly, all of these things are sort of independently happening. And what we saw was there was a sort of convergence. And what you saw was people who had been working on these kinds of disciplines quickly recognized that suddenly the components, the sensing components, their weight, their size, the amount of power they required, the computing that was available, all sort of made sense to put on a meter scale aircraft, for example. And now we could do these kinds of things. So I think it sort of works organically that way, rather than some sort of a formal method of like trying to think about risk and trying to use that to figure out what's acceptable.
Can you share the weight of the automation gear used in the Orchard drone, including the compute?
Yeah, so it's been a while. I don't know exactly, but I would say less than 5 pounds. Uh, yeah, less than 5 pounds. I mean, you can get that now. There's a couple of people. If somebody wants to contact me, I can tell you about where you might be able to find something like that. In 2 to 3 pounds now, you can do the same kind of thing.
So those were our final questions. Thank you so much, Sanjiv, for such an informative expert lecture. I know this is one that our teams can certainly continue to reference in the future because you offered so much information and so many resources. We look forward to your continued support. And teams, please remember to utilize herox.com/GoAERO, which is where we will be posting the recording of this webinar. We also have 3 expert lectures coming later this month, so please stay tuned for information on those. And Sanjiv, thank you again, and we look forward to continuing to have your support with GoAERO.
Great, thank you. Fantastic challenge. As I said, it's very unique, very relevant, and people who solve this problem will be will be not only training themselves, but will have some huge contribution to the state of the art.
Thanks very much, everyone. Take care.